What upward force would you need to exert on an 11.5 piece of murrelite? It's got a very unfortunate density, right? It's 1,666 kilograms per cubic meter, submerged in the Dead Sea, where water has a density of 1240. Which this is amazing, right? It means every cubic meter has 240 kilograms of salt in it, right? To keep it from sinking. Okay, so the first thing I want to do is I really need to know the volume of murrelite that I have here. So density is mass divided by volume. So therefore volume is mass divided by density, right? I mean density. 11.5 kilograms divided by 1666 kilograms per cubic meter. Okay. Yeah, and you'll see the units, the kilograms cancel. 1 over cubic meters is cubic meters, right? So 11.5 divided by, this will be hardly any cubic meters at all. 0.006927 cubic meters. That's my volume, right? That's what I'm solving for. Make our V's big, right? Because we're going to introduce velocity, which, we don't want to confuse that. Okay. So now we know the volume of it. Don't we have to figure out the buoyant force? Let's do that. Rho of the fluid, volume of the fluid, times G, right? So the density of the fluid is 1240. And that's kilograms per cubic meter. The volume displaced. Oh, sorry. All right. The volume displaced is this, right? This is, by the way, that's Archimedes' principle, right? Is that the object that has a certain volume displaces that volume when submerged, right? So 0.006927. That's cubic meters. And then times 9.81, and that's newtons per kilogram. Now you'll see what cubic meters cancel, the kilograms cancel, you'll end up with newtons. So that number that I have on my calculator times 1240 times 9.81. So the buoyant force, the upward force on the thing is 83.967, okay? And that'll be an upward force. The force of gravity on the piece of murrelite is going to just be mg, right? So that'll be 11.5 times, that's kilograms times 9.81. And so the force down is going to be 1112.815. Okay? And then we can set up an equilibrium expression. So here is the Dead Sea. Here's the murrelite. Okay? We have an upward force of 83.967 newtons. That's the buoyant force. So you have a downward force of 112.815. And then we have an unknown force, right? We know it's going to be up, but we'll just pretend that we don't know, right? And we set up an equilibrium expression, right? So positive 83.967 plus F. So unknowns, you just always say are F, minus 1112.815 equals 0, right? That is, the thing is neither accelerating up nor down, right? So this is Newton's, second law or something like that. Or we're just setting up a statics equation, right? And if you're paying attention, you'll notice that this has to be a positive number. And it's really just the difference between these two. So I'm going to go 112 minus this guy. So minus, and I end up 28.8. So the upward force is 28.8 newtons. Now, if you got to this point and immediately realized you had to subtract those to figure out this upward force, that's great. You don't need to set up an expression like this. But ultimately, if you don't understand it, well, then just set it up, right? What are the upward forces? What are the downward forces? Add an unknown force there, and that'll be the force that keeps it from accelerating down, which I guess we take that to be sinking. I am sinking. What are you sinking about? All right. That's a Berlitz ad, I think. You have to look at, I think it's called the German Coast Guard.